Thanks for tuning in. I'm your host, Jason Miller. Here today with a special guest. We have with us Professor Duncan Carlsmith, physicist at University of Wisconsin-Madison. But the reason he's here is that he also works at the CERN facility, the particle accelerator in Switzerland, that recently discovered the Higgs Boson God particle. Thanks for being here, Duncan.
Thanks for having me, Jason.
Duncan, tell our viewers something about your background, what you do as far as a professor, as far as CERN.
Sure. I'm a professor at University of Wisconsin-Madison, and there I teach physics, often to liberal arts students and engineers and physics majors. I've been working in elementary particle physics for my research for all my career, really, largely at Fermi Lab over the years outside Chicago, and now at the CERN Accelerator Laboratory outside Geneva, Switzerland.
Okay, great. Now, before we get into the meat of the matter, which is the Higgs boson, explain, if you would, to our viewers what the CERN facility is and what its purpose is, what it hopes to find, what has found already, except that we'll do Higgs boson separately.
Certainly. It's a large colliding beam machine. So it collides the nuclei of hydrogen atoms, which are called protons. And there are two beams. The machine itself is a circular ring of electromagnets, which guide the particle bunches around the accelerator and towards the collisions. So there are two counter-circulating beams at the machine. The machine itself is about 17 miles around and about 300 feet underground, so it's in a tunnel. And the way it works is fairly simple. You have a linear accelerator in which a particle that's charged like the proton surfs an electromagnetic wave and gets a little kick. And then you send it around the ring and the magnets guide it back through the linear accelerator, and you keep kicking and kicking and kicking and accelerate it. It's called a synchrotron machine. So much of the accelerator is really just guiding magnets which bring the particles back to their origin. These particular magnets are really a technological tour de force. They're all at liquid helium temperature and operated as superconductors. So it's quite an accomplishment to make such an array of these magnets and get them all to operate in synchrony.
So you have the particles coming in two different directions that you hope will collide, but they're extremely small.
Yes.
Is it that trillions of particles are coming at each other and several of them actually do meet and hit and collide?
They come in bunches, in what we call bunches, they're threads. Think of them as about a foot long and about the cross-section of a human hair. And you're firing these bunches at the speed of light towards one another. And they have to go 17 miles around and pass through one another over and over and over again. It's not easy.
Oh, it can be many revolutions, so
yes.
A few of them finally hit each other?
They hit as the bunches pass through, some hit, and then they go around again and collide again until they wear out, in effect. That's exactly what happens.
Particles wear out?
Well, until the bunches are depleted through the collisions of the protons. Yeah, so it takes, the acceleration process takes sort of an order an hour, and once the machine is fully loaded, it will run for an order a day until the beams are depleted. How many collisions do you hope to get? Trillions. We have a very high event rate. We get, and the brightness is going up and up and up, but we get of order 20 interactions every billionth of a second, every 25 billionths of a second. So it's sort of a billion interactions per second, and we run for a year, which is like 10 million seconds. We get a lot of collisions. And computers are used to analyze all this information. Absolutely, yeah. It's all on a huge electronic gadget. So the particles collide. their energy is transformed in various interesting ways into other kinds of matter and particles which travel quite a distance. And the collision point is surrounded by a very large detector complex, which in real time detects the particles moving away from the collisions at light speed. Takes a kind of digital image of the whole thing, the image constituting lots of little ions that are created in different kinds of materials and flashes of light and stuff. And all of that data is pipelined to a vast computer farm for event selection, and then further passed out around the world on something we call a grid computing. It's sort of a hyper network, if you will. I should say that that grid computing is a fairly new technology, and the University of Wisconsin has played a crucial role in developing the software that runs all that.
Fascinating. All right, I'm speaking with Professor Duncan Carlsmith about the Higgs Boson God particle. Stay with us. We're going to take a short break for a commercial. When we return, we'll discuss the Higgs boson that was recently discovered and go into detail about that. We'll be right back. We're back with Duncan Carlsmith, physics professor at UW Wisconsin, who also is a scientist working in CERN, Switzerland, on the particle accelerator. Mm-hmm. Okay, so let's go into that now. The Higgs boson, the big discovery, was several weeks ago, I suppose. They decided that it actually happened.
Quite a process, yes.
So tell us what it is and why it's so important.
Okay, you're going to have to bear with me while I explain it a little bit. I'll try not to give you too cheap an analogy. But first I have to tell you about matter, which is in general. So we know now from all the studies that have been done in the last 20 years, everything about the constituents of what I call normal matter, what technically is called baryonic matter, that's the stuff we're made out of. So you and I are made out of two kinds of something called a quark, which are the constituents of the nucleus of atoms, and then a lepton, which is called the electron and whirls around atoms. And different elements are made of different quark combinations in the nucleus and matching electrons that go around. What we've shown is that these are the lightest of an array of similar objects called quarks and leptons that appear in 3 generations. And they differ essentially only in their mass. So there's a heavy version of the electron called the muon and a still heavier one called the tau. And there are heavier versions of the quarks with funny names, charm and strange, top and bottom. And these heavy ones are able to decay spontaneously and transform their rest energy into lighter particles. So they decay spontaneously in very short time scales. And what's left are the relic light particles, the up and down quarks and the electron that we're made of. So a question is, what sets all the masses of these particles? And there's very strange, has been a very interesting, fascinating theory of this, which is called the Higgs mechanism, due to Peter Higgs and some others. And so now let me try to explain how that works. This theory says that the particles that we find, these quarks and leptons, just left to themselves would all be massless and move at the speed of light, at the maximum speed. But there is, in the dynamics of the vacuum, what we call the vacuum, something that behaves almost like a fluid, so that the particles slip through this and are slowed down. And something that happens in ordinary life that is familiar is like this, is when light traverses glass or water, it actually slows down by about 50%. And so these particles interact with this Higgs field medium in different ways, and they slow down from light speed and therefore appear to have mass. So in this theory, their rest energy is actually a representation of a new interaction with something in the vacuum, something quite mysterious. We call it the Higgs field, but we don't really know what it is. We don't know whether it's a superconducting, superfluid condensate of top quarks, or we really don't know what it is. But this theory, which sounds pretty crazy, it says in effect that space is filled with something mysterious, has had a number of really interesting predictions. In fact, it was invented to explain the masses of two very heavy particles and predicted their masses. And so we developed confidence in the theory ages ago, even though it sounds kind of crazy. So now that's the Higgs field, what its role is. We don't know what it is, but we know its impact on the quarks and leptons. So the Higgs theory has this interesting prediction that the Higgs field itself has a dynamics it can shake and move around. So the analogy I like to use is fish moving through water. So imagine you're a goldfish and you live in water. We think of that as the vacuum, and you don't know that it's water. And some smart goldfish says, you know, you live in water. And you know, goldfish will say, nah, no, I don't need that idea. But the fish says, I'm going to prove it to you, because if you live in water, I can make sound in the water. I can shake the water and make sound waves, and then you'll be able to have sonar and talk to one another. So in the Higgs theory case, there's a kind of a sound wave that can be made in the Higgs field. And the way you make such a sound wave is you take a very heavy particle, which is slowed down a lot, so linked to the fluid very closely, and you shake it up and down in effect, and you make a sound wave. And the energy of that sound wave appears as quantized particles, which are called Higgs particles. So that's why we're looking for this. We're trying to be the fish that sort of demonstrates that the stuff really exists and has a dynamics that we can probe. So at the Large Hadron Collider, what we do is we make very heavy particles, and as they burst into existence, it's kind of like shaking something in water. They radiate a kind of a sonic boom, a kind of a cone of waves in the Higgs fluid, and associated with that, then we see, associated with the heavy particles, we look for the Higgs particles to try to verify this theory.
Well, so when these particles collide and they make these images on the computer, sort of like sparks or whatnot, they each have their own sort of signature. You can tell which particle is which based on this?
Yes, they behave, when they pass through ordinary matter, they behave in different ways. So, for example, an electron will, as it passes through matter, will knock other electrons left and right. And a photon might go straight through a transparent medium and non-interact in that way. Some particles, like a muon, will plow through meters of steel and just go off into space. So yes, each has their distinct signature. So we sort out all the different particles that are made and then reconstruct what happened in any given event, any given collision.
Well, you know, I realize this is a new sort of discovery, but do you see way down the road spin-offs, technological spin-offs that might derive from this God particle?
You know, at this point, anything direct use of the Higgs field as we know it today, it would only be speculation. It's what we're discovering more and more is that all we know about matter is just really the tip of the iceberg. The normal matter that you and I are made of, and that I've studied forever, is very well understood. We now know is really just a small instance and maybe just frosting on a very large cake of what's in what we call space. This Higgs field is one very mysterious aspect. Other ones include dark matter and dark energy that we know play a very important role in the evolution of the universe.
Let's talk about dark matter next, but we have one more commercial. Stay with us. We'll be back in one moment. We're back. We've just been discussing the Higgs Boson God particle, and next at CERN, the particle accelerator, from what I read, is they would like to do experiments on dark matter, which you referred to just before the commercial.
Mm-hmm.
Tell us about dark matter, what it is, and what you suppose they would try to find.
Sure, absolutely. First, what dark matter is. It's been known for quite a long time that galaxies that are spinning don't contain enough luminous normal matter to explain the rate at which they spin. An object like our solar system moves around the center of our galaxy at a certain rate, and if there's more matter, more gravitational force on it, then it'll move faster. When you compare how much force the luminous light matter, if you will, how much gravity there is there, and look at the speed, you discover that there really must be some non-luminous source of gravity. That was the first evidence for a dark matter component to a galaxy. Now we observe the same effect by seeing how a galaxy deflects light as it goes by it. That's through Einstein's gravitational deflection of light, or gravitational lensing. So we observe the same effect both in matter moving around and in light going by, that there's some dark matter in galaxies. In cosmological theory now, this has been put into lots of models, and what we learn from the entire history of the universe is there's actually 5 times more of this dark stuff than normal stuff. And we are clueless really what it is. One idea is that rather like normal matter is sort of a relic of lots of particles were made in the early stages of the universe, and the heavy ones decayed and left a little bit of normal matter left. A similar idea is that there's a spectrum of other particles, perhaps something called superparticles in a so-called supersymmetric theory, with the lightest particle into which they all decayed, and kind of a relic particle of that sort could be the origin and principal constituent of dark matter. So the theory is that we might actually have enough energy at the Large Hadron Collider to make these particles directly out of the energy that in the collisions. So the experiments, and there are 2 large experiments, the CMS experiment and the so-called ATLAS experiment, are looking for events which would, in a characteristic signature of a dark matter would be, you would make a dark matter particle maybe in pairs. One of them would just move away, and energy would apparently disappear in association with other particles that are made. That's one signature. So we look for that kind of event as a dark matter candidates.
That's so interesting. We may have forgotten one thing that probably most of our viewers are familiar with, but maybe some aren't. The Big Bang theory. Is it still a theory?
We can call it a theory.
All right. Because everything derives from that. The Higgs boson, dark matter, luminous energy, everything is luminous energy, luminous matter. Would you explain to our viewers just the basics of the Big Bang?
Sure. Principal earliest evidence is you look out at galaxies near us and you discover that they are moving away from us. And you measure their velocities through effectively the Doppler effect of their light. Run them clock backwards and you discover there was a time when they were all on top of one another. And that was about 13.5 billion years ago. At that time, the universe, by extrapolation, was very hot and dense. And if you just continue to extrapolate, you arrive at a singularity where the density is infinite, and that's called the Big Bang. So we can now start close to the Big Bang and run the clock forward, knowing all the physics of high-energy particle collisions and high-temperature matter, and put in dark matter and now something called dark energy, and derive a whole history, predict the evolution of galaxies and stars and planets and life itself in principle.
So just to be clear, so at the very beginning, there was everything that we see or know of in the universe was in one place at one time, and it was infinitesimally small.
Yes.
Well, infinitely small, but it must have been a little bit.
Right.
So
right. We can't extrapolate all the way back to zero and infinity. We don't understand the physics that was happening in the interplay of particles, even the spectrum of particles that might have existed and been governing the universe at these very early times.
It's really quite amazing. So to have everything in the known universe in one small size of a pinhead, maybe, and from that explosion came everything
that we can see today
in the universe.
That's correct, within the visible universe.
It's amazing.
It's really astounding.
Well,
and there are things in it which we don't understand. So we know dark matter played a crucial role. We can see even the sound waves in dark matter. They've left an imprint on the galaxy distributions that are out there. And we can see their influence on light from the early universe. When you look out, we see extremely redshifted light from a time when the universe became just transparent and ceased to be a plasma. And we can see the imprint of the various components of the universe on the distribution of that light too. So we can look back to the very early universe in various ways and verify our models of what was going on.
Well, you know, the Big Bang, the Higgs boson, dark matter, I'm curious what the religious implications are. If physicists in general tend to be spiritual once they learn about these different amazing things.
I think scientists and maybe physicists, I can't speak for everyone, tend to be pretty much in awe and humbled by what we discover in the universe. We know how little we know. And we know there's just tremendous and exciting things to discover. And the Higgs field is a big mystery that we really want to know more about. How that relates to conventional religion is probably not a question that scientists or physicists tend to spend a lot of time on. But I don't think anything that we do is really, or the knowledge that we gather from scientific studies is at all, negative in any way about religion. Religion is a personal thing, and many scientists are actually religious people.
Well, I mean, I'm separating religious from spiritual.
Mm-hmm.
This is not necessarily a set organized religion that they might have an interest in, but just a belief that there was a prime mover, we'll say, when they discovered these kind of things.
Yeah. The odd thing is, there's so many mysteries. We don't know. You asked me before whether the universe will expand forever or go back to a big crunch, or whether there was really just one origin of time. We don't know the answer to those questions. In fact, we also even know that in principle there are things we can never know, because light only travels at a fixed speed, and as we look out back in time, we see light from earlier times, and there comes a point, we call it a horizon, beyond which, in principle, we cannot see. So if that is all true, we can't even know the entire universe. We're limited by physical laws. I may be wrong. The laws may be wrong. We discover new things. But there are a lot more questions than there are answers.
It's fascinating, fascinating. Well, thank you so much for coming here today and talking with us, Duncan. I appreciate that.
Thank you very much.
And thanks to our viewers for joining us today here at NEWSDESK. Tune in next week for another episode of NEWSDESK. That's Channel 95 Analog, Channel 991 Digital, on YouTube at NEWSDESK WYOU. If you're watching on TV now, up next is Democracy Now! With Amy Goodman. This is Jason Miller broadcasting from Madison, Wisconsin. Bye for now.